All right, so are you ready to dive deep today?
I'm always ready to dive deep.
Excellent.
Let's do it.
Okay, so today we're tackling concentration and solubility.
Mm-hmm.
And I have a series of slides that you sent over.
Yes.
And it looks like you're prepping for some kind of like a real chemistry challenge or something.
Yeah, a little bit.
But don't worry, because by the end of this deep dive,
Yes.
you will be a pro at solutions, solutes, solvents,
It's going to be great.
and all those factors that make things dissolve
Yeah.
or not.
That's right. And trust me, this stuff is, it's way more interesting than it might sound at first.
Yeah.
We're not just talking about sugar like disappearing into your coffee here.
Yeah.
We're talking about the foundation of how our world works at a molecular level.
Okay, so I know we've all kind of heard these terms before, right?
Right.
Like solubility, dissolves in water, big deal.
Yeah, okay.
But like these slides start hinting at some pretty wild stuff. Like, did you know that solids and solvents aren't always solids and liquids?
Exactly.
We're talking about like gases dissolving in liquids, solids dissolving in gases.
Yeah.
Like it goes every which way.
It really does. It's easy to get stuck
Yeah.
thinking about that, like classic saltwater example.
Yeah.
But solubility goes way beyond that.
Right.
Think about, like, the air we breathe.
Okay.
It's a solution of gases
Oh.
with nitrogen as the solvent and things like oxygen, carbon dioxide, and other gases as the solids.
Whoa. Okay, so it's not as simple as
Yeah.
just the amounts of each substance.
You got it.
Okay.
Yeah, it's about which substance is doing the dissolving,
Okay.
which kind of keeps its physical state,
Okay.
not just the quantities involved.
Got it. Okay, so we've got our basic definitions sorted,
Yeah.
but then these slides dive into like factors affecting solubility and things get really interesting. We're talking about temperature, pressure.
Yeah.
It's like a whole dance of variables.
It absolutely is, and those variables can have some pretty dramatic effects.
Yeah.
Take temperature, for instance.
Okay.
Think about trying to dissolve sugar in, like, iced tea
Okay.
versus hot tea.
Okay, yeah.
You can pack way more sugar into that hot tea
Totally.
because that higher temperature increases the kinetic energy
Right.
of the water molecules, making them much more efficient at breaking apart and surrounding those sugar molecules.
So hotter generally means more dissolving power.
For solids and liquids, yeah.
For solids and liquids.
Yeah.
I'm guessing it's different for gases, though.
Yeah.
Because my soda always seems to go flat faster on a hot day.
You're exactly right.
Really?
For gases dissolved in liquids,
Okay.
it's actually the opposite.
Oh.
Higher temperatures mean less solubility.
Oh.
Think about, like, those bubbles escaping from your soda.
Yeah.
As the temperature increases,
Yeah.
those gas molecules get more energetic and want to break free from the liquid.
So that's why warm soda is sad soda.
Yes.
Got it. These slides also mention this like dissolves like principle. What is that all about?
Okay, so basically, substances with similar chemical properties tend to dissolve in each other.
Okay.
So polar substances, which have like a slightly positive end and a slightly negative end,
Yeah.
almost like tiny little magnets,
Uh-huh.
love to dissolve other polar substances.
Wait, so water molecules are like little magnets clinging to each other?
They kind of are.
That's adorable.
And that's why water, which is a polar substance, is so good at dissolving other polar substances like salt.
Right.
But it struggles with nonpolar substances,
Okay.
like oil, which don't have those distinct positive and negative ends.
So that's why my salad dressing's always separate.
Precisely.
The oil and the water just can't get along
Yeah, they're like,
because they're not attracted to each other on like a molecular level.
they're like two different dance crews trying to
Right.
perform together. Their moves just don't mesh.
I love that analogy.
Yeah.
Okay. The slides also mention surface area and stirring.
Okay.
How do those play into the whole solubility game?
So these factors don't affect how MuCH can dissolve,
Okay.
but they can speed up or slow down the process.
Right.
Think about it this way. If you have a big chunk of sugar,
Yeah.
it's going to take longer to dissolve than if you grind it up into a powder.
Right.
Smaller particles means more surface area,
Okay.
which means more contact between the solute and solvent,
Gotcha.
and that speeds things up.
So if I'm like in a rush to sweeten my tea,
Yes.
I should be using powdered sugar.
Exactly. And stirring or shaking has a similar effect.
Okay.
It just helps those solute and solvent molecules bump into each other more often,
Right.
speeding up that dissolving process.
Okay, so we've covered the basics and some of the key factors
Yeah.
influencing solubility, but the slides are about to take us into some seriously cool territory. Saturation and supersaturation.
Right.
This is where things get a bit magical.
You're not wrong. Imagine a solution that's holding on to more solute
Oh, wow.
than it theoretically should at a given temperature.
Okay.
It's like a delicate balancing act, a
Yeah.
temporary state of too much of a good thing
Right.
that can be tipped over with the slightest disturbance.
Oh, wow. Okay, hold on.
Yeah.
I need to wrap my head around this.
Okay.
So a saturated solution is like my tea when I've added like the maximum amount of sugar it can hold anymore, and it just sinks to the bottom, right?
You got it.
Okay.
That's the saturation point.
Right.
No more solute can dissolve at that specific temperature.
Right. Okay.
But supersaturated solutions are different.
Okay.
They're actually holding more dissolved solute
Okay.
than they should be able to.
Oh, okay.
It's kind of like a super concentrated concoction.
Wait, how is that even possible?
It's all about a careful trick of temperature.
Okay.
You dissolve the solute at a higher temperature, then you carefully cool it down.
Okay.
And the excess solute stays dissolved.
Wow.
But the solution becomes unstable,
Yep.
like a house of cards waiting to topple.
Whoa. So what happens if you disturb it?
That's where the magic happens.
Okay.
Add a seed crystal,
Okay.
scratch the container, even just a tiny vibration,
Oh, wow.
and bam,
Okay.
crystallization happens
Oh, wow.
rapidly,
Yeah.
with that excess solute coming out of solution almost instantly.
That sounds mesmerizing.
It is.
It's like watching like a sudden snowstorm in a glass of water or something.
Yeah. And the slides also mention that this crystallization releases heat.
Oh, really?
Why is that?
Yeah, why is that?
Well, remember how dissolving usually absorbs energy,
Okay.
making the solution cooler?
Yeah.
Well, when that solute crystallizes out of solution,
Right.
all that stored energy gets released back into the surroundings as heat,
Okay.
kind of like an energy boomerang.
So it's like a reverse dissolving process energy-wise.
Yes.
Cool. Now the slides are introducing this concept of electrolytes.
Go on.
What exactly are they?
So electrolytes are substances that, when dissolved in water, produce ions.
Okay.
And these ions are what allow a solution to conduct electricity.
Okay.
You know, those sports drinks they always push for athletes?
Right.
They're packed with electrolytes.
Yeah.
And that's not just marketing hype.
Oh, okay.
Electrolytes are vital for our bodies
Yeah.
because they regulate so many critical functions.
So electrolytes are like the electrical wiring of our bodies?
Kind of.
Okay.
They're essential for maintaining fluid balance,
Right.
keeping our muscles and nerves firing properly,
Wow.
even regulating our heartbeat.
That's a lot of responsibility for something that just dissolves in water.
I know, right?
And the slides mention salts, acids, and bases as common examples. Is there a difference in how well they conduct electricity?
Absolutely. That's where the concepts of strong and weak electrolytes come in. Strong electrolytes like table salt
Right.
essentially ionize completely
Right.
when dissolved in water,
Okay.
meaning they break apart into their constituent ions.
Yeah, okay.
They're the powerhouse conductors of the electrolyte world.
Okay.
Weak electrolytes, on the other hand,
Yeah.
only partially ionize,
Okay.
meaning only a fraction of their molecules
Right.
break apart into ions when dissolved.
Right.
They're still important, but they don't conduct electricity as effectively.
So the more ions in a solution,
Yeah.
the better it conducts electricity.
Exactly. It's like having more lanes on a highway.
Right.
More ions means more pathways for those electrical charges to flow.
Got it. Okay. This is all starting to make sense.
Right.
But my brain is definitely getting a workout.
That's a good sign.
Okay.
It means we're getting somewhere.
Okay. Okay.
And trust me, it's about to get even more fascinating
Uh-oh.
as we delve into the unique properties of water itself.
Ooh, I'm intrigued.
Okay.
Let's keep this deep dive going.
Let's do it.
Yeah.
So we've talked about solutions in general.
Right.
But now let's zoom in on like the most important solvent on Earth,
Okay.
water.
Water.
Even plain old Hubs 2 Subo
Yeah.
has some surprising tricks up its sleeve.
You mean besides the fact that it makes up like 70% of our planet and
Right.
keeps us all alive?
Exactly.
What else could there be?
Well, did you know that water can actually act as both an acid and a base?
Wait, seriously?
It's true.
So even pure water
Yeah.
has a little bit of acid and base in it.
It does.
That's wild. How does that even work?
So it's thanks to this process called autoionization.
Autoionization.
Basically, imagine two water molecules bumping into each other.
Okay.
One acts like an acid,
Yeah.
donating a proton that's an H+ ion,
Okay.
and the other acts like a base,
Right.
accepting that proton.
Okay.
This creates two new ions,
Mm-hmm.
hydronium H3 subo plus
Okay.
and hydroxide OH.
So it's like a little water molecule swap party.
Exactly.
Okay.
And this swap party,
It's happening all the time in water.
wow.
It's a dynamic equilibrium,
Okay.
meaning the reaction is constantly going back and forth,
Yeah.
but the concentrations of those hydronium and hydroxide ions stay balanced
Okay.
in pure water at a given temperature.
So there's this constant like dance of ions happening in every drop of water.
Yes.
That's pretty mind-blowing.
I know, right?
The slides also mention this thing, an equilibrium constant CRO,
Okay.
and specific concentrations for these ions at 25 degrees Celsius.
Right.
What is the significance of that?
So that equilibrium constant CRO
Right.
is like a chemical snapshot telling us how much autoenginization is happening at a specific temperature.
Gotcha.
At 25 degrees Celsius, CRO is a tiny number, 1.0 by 10 to the negative 14th,
Wow.
meaning the concentrations of hydronium and hydroxide ions are super low,
Okay.
but they're still there,
Right.
constantly playing their roles as acid and base.
So even though pure water seems perfectly neutral to us,
There's a whole lot of action going on at the molecular level.
it really is.
Now, these last few slides seem to be focusing on this concept of percent ionization.
Okay.
How does that fit into the big picture?
So percent ionization is a way to quantify how much of a weak electrolyte actually breaks apart into ions when it's dissolved.
Right.
We can calculate it by dividing the concentration of ionized acid by the initial concentration of acid
Yeah.
and then multiplying by 100%.
Okay.
It's a percentage.
So if a weak electrolyte is like a shy dancer, only venturing onto the dance floor occasionally, percent ionization tells us how much time they actually spend dancing.
That's a great way to put it.
Okay.
And just like some dancers are naturally more outgoing than others,
Right.
the percent ionization of a weak electrolyte depends on its chemical personality.
Okay.
How much of it is around its concentration and
Yeah.
the solvent it's in.
So a higher percent ionization means more ions are present,
Yes.
making the solution a better conductor of electricity.
You got it. Strong electrolytes are those bold dancers who are always out there,
Okay.
fully ionized and ready to conduct electricity, like pros.
Right.
Weak electrolytes, on the other hand, are a bit more hesitant.
Okay.
So their conductivity is weaker because they don't form as many ions.
Oh, all right. That makes sense.
Yeah.
It's amazing how these seemingly abstract concepts
Right.
have such real-world implications.
Yeah.
From the function of our bodies to the behavior of solutions in a lab.
It's true.
Yeah.
And speaking of real-world implications,
Okay.
that last slide in the set you sent
Yeah.
has a bunch of questions
Oh, yeah.
that really put our understanding of concentration and solubility to the test.
Oh, yeah. It's like they knew we were going to have this conversation.
I think they did.
Let's dive into those questions and see what other fascinating insights we could uncover.
Let's do it.
All right. The first one asks,
Okay.
what are some factors that can affect the solubility of a substance? It feels like we've covered this one pretty thoroughly already.
Yeah, I think so.
We talked about temperature, pressure,
Yeah.
the
Yeah.
dissolved principle,
Yeah.
surface area, and stirring, anything we missed.
I think we hit all the major players there.
Okay.
It's just a good reminder
Right.
that solubility isn't a one-size-fits-all concept.
Right.
It's a delicate dance between the solute, the solvent, and the surrounding conditions.
Okay. Next question.
Okay.
How can you determine if a solution is saturated or supersaturated?
Okay.
This one sounds a bit more challenging.
Yeah.
Like, how can you tell if you've hit that tipping point between just enough solid and way too much?
It can be tricky,
Yeah.
especially with supersaturated solutions,
Oh, right.
which can appear perfectly stable
Right.
until they're not.
Yeah. Yeah.
One way to check for saturation is to add a tiny bit more solute.
Okay.
If the solution is unsaturated,
Yeah.
that extra solute will dissolve. If it's saturated, it'll just sink to the bottom,
Right.
like adding more sugar to already sweet tea.
Right. Okay.
Yeah.
But what about supersaturated solutions?
Uh-huh.
How do you test for those without
Right.
setting off like a sudden crystallization avalanche?
That's where the fun begins.
Okay.
With a supersaturated solution, even the slightest disturbance
Yeah.
can trigger that dramatic crystallization process.
Right.
Adding a tiny seed crystal of the solute
Okay.
or gently scratching the inside of the container
Okay.
can kickstart the whole thing.
So it's like a delicate balancing act where
It is.
even a slight nudge can send everything crashing down.
Exactly. It's a visual reminder that those excess solute molecules are just waiting for an excuse
Yeah.
to break free and form those beautiful ordered structures we call crystals.
Okay, the next question is a bit more conceptual.
Okay.
How does the concentration of a solution affect its properties, such as boiling point or freezing point?
This is where we get into colligative properties.
Yes. Colligative properties.
Which are properties of solutions that depend solely on the concentration of solute particles,
Okay.
not on the identity of the solute itself.
So it doesn't matter if it's salt, sugar, or something else?
Exactly.
Just how much of it there is.
Yeah, it's like a chemical democracy where every solute particle gets an equal vote.
That's fascinating.
Yeah.
What are some examples of these colligative properties in action?
One of the most well-known is boiling point elevation.
Okay.
Adding a non-volatile solute to a solvent
Uh-huh.
actually increases the boiling point of the solution compared to the pure solvent.
Wait, so adding salt to water when cooking pasta actually makes the water boil at a higher temperature?
It's true.
I always thought that was just an old wives' tale.
Nope, it's science.
Okay.
Those solute particles disrupt the vapor pressure of the solvent,
Yeah.
making it harder for the liquid to escape into the gas phase.
Okay.
So you need more energy,
Right.
and thus a higher temperature
Gotcha.
to reach the boiling point.
So it's like the salty particles are creating like a little obstacle course for the water molecules trying to escape as steam.
Exactly.
What about freezing point?
Uh-huh.
Does concentration affect that too?
It absolutely does.
Really?
Adding a solute to a solvent actually lowers the freezing point of the solution
Okay.
compared to the pure solvent.
So it goes the other way. Yeah.
Yes, this is called freezing point depression.
Freezing point depression.
Think about salting icy roads in the winter.
Right.
The salt dissolves into the ice,
Yeah.
disrupting its structure and lowering its freezing point.
Oh, wow.
So it melts even when the temperature is below 0 degrees Celsius.
So it's like the solute particles are interfering with the water molecule's ability to form those nice organized structures that make up ice.
Exactly.
So to sum it up,
Yeah.
adding a solute to a solvent increases the boiling point
Yes.
and decreases the freezing point.
Precisely. And these effects are directly proportional to the concentration of the solute.
Okay.
The more solute particles there are,
Right.
the greater the boiling point elevation and the lower the freezing point depression.
Wow, that's like a little chemical magic trick.
I know, it's pretty cool.
Okay, the last question on the slide asks,
Good.
why is it important to understand the concept of solubility in chemistry? I think we've been answering that question throughout this entire deep dive.
I think so too.
It seems like solubility is woven into so many different aspects of chemistry, from the everyday to the extraordinary.
It's absolutely fundamental.
Yeah.
From understanding how medications dissolve and are absorbed in our bodies,
Right.
to developing new materials and technologies,
Right.
solubility plays a crucial role.
Yeah.
It's a key that unlocks a deeper understanding of how our world works at a molecular level.
It's amazing to think that something as seemingly simple as a substance dissolving in another can have such far-reaching implications.
It's true.
But before we wrap up this fascinating journey
Yeah.
through the world of concentration and solubility,
Okay.
I have one final question for you.
Okay.
It's something that's always puzzled me.
Okay.
And it goes back to that, like, dissolves, like, principle.
Uh-huh.
Why do you think oil and water don't mix?
That's a great question. And it takes us right to the heart of molecular interactions
Okay.
and those adorable little water magnets we talked about earlier.
Yeah, because those little water magnets are stuck in my head now.
I know, right?
So cute.
Well, oil, on the other hand, is a non-polar substance.
Okay.
Its molecules don't have those distinct positive and negative ends,
right.
so they don't have that same strong attraction to water molecules.
So it's a matter of attraction.
Yes.
Water molecules are more attracted to each other
Uh-huh.
than they are to oil molecules, so they just stick to their own.
Exactly. When you try to mix oil and water,
Yeah.
the water molecules cling together
Right.
and the oil molecules clump together,
Yeah.
refusing to form a homogeneous solution.
Right.
They're just not compatible on a molecular level.
Right.
It's like trying to mix magnets and marbles.
Mm-hmm.
They just won't blend together smoothly.
That makes so much sense.
Good.
So it's all about those underlying molecular interactions, those tiny forces of attraction and repulsion that govern how substances behave.
It is.
This deep dive has been a real eye-opener.
It has been a fascinating journey.
Yeah.
And it's a reminder that even the most familiar phenomena,
Right.
like mixing oil and water,
Yeah.
can reveal incredible insights into the workings of our world at the molecular level.
It's true.
But before we say goodbye,
Yeah.
I have one final thought for you, dear listener.
Okay.
Something to ponder as you continue your own explorations in the world of chemistry.
Okay, so lay it on me. What's the final, like, mind-blowing thought I need to take away from this deep dive.
Well, we've been focusing on like how and why things dissolve. Right. But what about those cases where solubility is actually a problem?
Okay.
Think about hard water, for example.
Okay.
All those dissolved minerals
Yeah.
can cause all sorts of issues, from scale buildup in pipes
Right?
to making it harder for soap to lather.
Oh, yeah. I've definitely battled like hard water stains in my bathroom.
Oh, for sure.
So in those cases, we're actually trying to decrease solubility, right?
Exactly.
Okay.
And there are a bunch of clever techniques for doing just that.
Yeah.
Water softeners, for instance, use ion exchange
All right.
to swap out those pesky calcium and magnesium ions for sodium ions,
Okay.
which are much less likely to cause problems.
So it's like a little chemical switcheroo, making the water less hard and more friendly to our plumbing and our skin.
Precisely. And there's another cool trick that takes advantage of solubility to purify water.
Yeah.
Reverse osmosis.
Reverse osmosis, that sounds intense.
It kind of is, but it's actually pretty elegant. You apply pressure to force water through a semi-permeable membrane.
Okay.
Essentially pushing it from a high concentration solution, which is like the impure water, to a low concentration solution.
Okay.
The pure water.
So the membrane acts like...
Yeah, it acts like a super selective bouncer.
Right.
Only allowing the water molecules through
Right.
while blocking those dissolved impurities.
So it's like filtering out the bad stuff by forcing the water through like a molecular sieve?
Exactly.
Okay.
And that's just one example of how understanding solubility can help us solve real-world problems.
Right.
From cleaning up contaminated water sources to developing new drug delivery systems.
Wow.
The applications are practically endless.
This deep dive has been a real revelation.
I know, it's pretty cool stuff.
I feel like I've gone from basic solubility to like advanced water purification in the span of a single conversation.
It's amazing how interconnected these concepts are.
It really is.
And it's a reminder that even something as seemingly simple as a substance dissolving in another can hold the key to understanding and addressing some of our most pressing challenges.
I'm definitely walking away from this with a newfound appreciation for the power of solubility.
Me too.
Well, thanks for taking me on this incredible journey.
It's been my pleasure. Keep exploring, keep asking questions.
Yeah.
And who knows what other fascinating discoveries await.
And to you, dear listener, thanks for diving deep with us. Keep those curious minds engaged, because there's always more to learn, more to uncover, and more to marvel at in the amazing world of chemistry. Until next time, stay curious.